Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
But we'll be looking at virtual work for this particular problem. We want to determine theta for equilibrium and also find stability for the equilibrium position. Okay, this is point A. Uh, C is a bar AC, right? Okay, and we have this angle here, theta. Okay, and we have the weights. We are given uh, okay, the weights of the this bar will act at that point to that point rather, and we're given here to be 2 meters, 2 meters. Sorry, and this is 2 meters as well. Okay, now we can. There's a spring here, a spring force there, and let's call it F source with S force, and the displacement. Let's call it S in that direction. We can have the we take A as our datum. Okay, we can establish a Y, call this Y, okay, that height. All right, you can see that we're going to have a negative and potential energy for the bar. All right, so if we consider the bar now, this is the bar AC. Y is going to give us 2 plus 2, 2 plus 2, which is the length actually, which is actually 4. Okay, cos theta. 2 plus 2 over 2 because the weight will act through half of it. So in other words, we are going to have the y is equals to 4, sorry, 2 cos theta. Okay, so that's what we're going to have. So that we have the potential, gravitational potential uh, energy. Give us, said is negative. It's going to give us actually negative. Okay, so that for the spring and the weight, note that the weight is given to the mass is given to us. Okay, as uh, 100 kg. All right. So if we multiply this by 9.81 by 9.81, 9.81 can get the weight, which should be actually equal to 981 Newton. So take note of that. All right. So that for the spring, we are going to have S. It's going to give us 2 sine, okay, 60 degrees, okay, because we are given that theta when on stretch is 60 degrees, okay. It's going to give us 2 sine 60 degrees, okay, minus 2 sine theta, okay, 2 sine theta for you to know the displacement, okay. So that's what we'll be about. All right, okay. This is theta you don't know that you are looking for now. So when you do this, you get the displacement. And of course, when you bring this one out, it's still similar saying is 2 2 sine 60 is 60 degrees, 60 degrees. okay, minus sine theta, minus sine theta. Okay, so that's what you are going to have there. Now V, the elastic potential energy is just the same thing as this times S over 2, which is something as K squared over 2. All right. So if we come, so V, the potential function is this gravitational potential plus elastic potential energy, so that we now have V to be equal to minus W y. Of course, we have figured out W already. It's 981. Okay, Newton, 91 Newton. So plugging in values and okay, doing your calculation, and plugging in the spring stiffness is given at 500 Newton per meter. Okay, we are going to arrive at minus 1962, 1962 cos theta, plus 750, okay, minus 1732, 32 sine, okay, sine theta plus 1000 sine square theta, sine square theta. So we have that. All right. So if we for our equilibrium position now, for equilibrium position, the V, the theta, set it to 0. That will give us 19. Give us 19. What that's 196 to 1962 sine theta, minus 1732 cos theta, plus 1000, okay, plus 1000 sine 2 theta, sine 2 theta. So you're going to have that, okay. Then you can just, but we know that sine 2 theta is equal to 2 sine theta cos theta. So when you do that, you can plug that into equation into there, and from trial and error, you're going to arrive at theta to be equal to 24.6 degree. Okay. Then for the stability, For the stability, we take the second, we'll differentiate again the second time with respect to theta. Yeah, so that to do that, please remember that this particular function, this one particular, is set to 0 before we solve. All right. So we solve for this one. We are going to arrive at 19 cos theta cos cos theta. Okay, plus 11732 sin theta sin theta. Okay, plus 1002 plus 1000 times 2 cos 2 theta times 2 cos 2 theta. Okay, now we know that sin theta cos theta is in that half sin 2 theta. Okay, so that's how we got to come to there. So that, all right, so that we can now have, if you solve this one, we are going to arrive plugging in our value for our equilibrium position. We are going to, which is 24.6. We'll have this to be equal to 3 8 3811, okay, 0.75. And you can see that this is clearly greater than 0, and that means we are talking of a stable equilibrium. So these are the values